seismic insights within geomagnetic and ionospheric data. Now we know that electromagnetic precursors have been considered a promising means of earthquake prediction. However, there is an unsolved problem of how to find persistent earthquake-related precursor signatures in geomagnetic as well as ionospheric data. A major obstacle has been the difficulty in excluding the space weather effects that account for most variations in these data sets. So the team turned to ML to answer this question. I wish both teams good luck with their closing presentations.
Hello, everyone, and welcome to the Seismic Insights within Geomagnetic and Ionospheric Data Team Challenge. So, if you haven't grasped it from that catchy title, we're talking about earthquake forecasting. And earthquake forecasting could help prevent tens of thousands of deaths per year. And now, I realize we have a largely Silicon Valley-based audience, so I'll translate that to it also being able to reduce our costs in $34 billion annually. There have been mounting circumstantial evidence from recent case studies for precursors in unconventional data sources. Now we come back to those words that were in the title. We're looking at the geomagnetic field which surrounds the Earth and the variability of which we can measure from stations on the ground. We're also considering the ionosphere, which is a layer of charged particles that lies between 80 and 600 kilometers above the Earth's surface, the density of which we can probe with GPS signals. Okay, so to confront this challenge, we've assembled the mighty team of Andy Gallidevra and myself, Luke, along with our advisory faculty with experience ranging from space weather through to machine learning. So what could possibly go wrong? Unfortunately, the small signals we expect to detect from earthquake signatures are swamped by the vastly larger signals emanating from the sun, which cause the beautiful aurora, but in our case, are a large source of noise. So imagine you have a needle, which is our little earthquake signatures, and amongst the haystack of other signatures coming in from mainly the sun. Just to add some interest, we also don't know what a needle looks like. So our first step was trying to identify the nature of the signal we're looking for. To do that and mitigate for other space noise, we looked at a whole range of earthquakes from around the world that you can see on the left here, and filtered them for large earthquakes, so magnitude above 7.5 events. And we looked first at a more accepted phenomenon, which is gravity waves after the event itself. And right enough, we found that consistently we can see a disturbance here on the right-hand side in the ionosphere in the hour to hour and a half after an earthquake. So, having validated this concept, we then moved to looking towards precursors. And what we discovered is that precursors are much more dependent on location and earthquake type. So here we have magnitude above 7 earthquakes from the Japanese region, and you can see that between 3 and 7 hours prior to the earthquake, there's a consistent drop in ionospheric density for these large events. So it's not as obvious as a signal for the aftershocks, but it does give us some hope that building a more complex model may be able to tease out these signatures for particular events. So we've identified what the needle might look like. So let's build the haystack. So we assemble our data sources that we've talked about previously, and through some unfortunately non-trivial feature engineering and time alignment to have the appropriate data for the earthquakes, we optimize to get to what we call our machine learning ready data. So, okay, we know what the needle looks like. We've got the haystack, and now we'll pass you over to Andy to tell you how we're going to look for it.
Thank you, Luke. This is a really tough problem. So we've actually attacked it in 2 different ways. The first is a direct method. So we're designing models here to predict if an earthquake has happened or if it will happen. The second method is indirect. Do earthquakes cause anomalies that will mean models of the ionosphere will give us terrible results? And can we use that discrepancy to then say an earthquake has happened or will happen? For the direct approach, we've tested an entire suite of models, from simple linear-based models all the way through to those based on deep learning. Ultimately, the performance was mixed, and the results for the best performing model are shown on the left. For context, I've included here the accuracy of a coin flip in this case. So for earthquakes greater than magnitude 6, we get slightly better accuracy than if you flip a coin in this setup. For slightly larger earthquakes, so those larger than 7, the performance goes up a little bit more. One of the things that we wanted to test, though, with this is whether this is a problem with the models and whether they can identify the patterns we need. So we designed a test with synthetic data where we put in earthquake signals that don't really exist. And then we tested our models on that. And the performance there was much, much better. So we're looking at performance now of about 96%. Ultimately, this leaves us with 2 options from this avenue of attack. Either the signals are too small in our data, or the data are not good enough to resolve them, or we need more data. We need better data and more of it. Okay, so can our indirect approach make some progress in this? Earthquakes are a regional disturbance, so we designed a regional ionospheric model to test this. The model uses the outer region here, so the outer grid here, outlined in red, to predict the properties of the ionosphere in the center box. Here we're showing it for an earthquake in northern Japan. On the right here, I'll animate how the model error changes over time. If the model is perfect, it will be a horizontal line on the 0 line. But realistically, we expect it to wiggle around this green zone here. So what we see is that's true before the earthquake, generally for this case. But then after the earthquake, about 10 minutes after it, the model performs catastrophically badly. And that's actually excellent. We can use this large error in the model to say that something strange has happened in the central zone. In this case, an earthquake has happened. These are the gravity waves that Luke mentioned earlier, messing with the ionosphere, meaning the model's predictions aren't as good. So, can we use the same approach to predict earthquakes? Here we have a very similar model, again over northern Japan, and again we're using the outer regions to predict the middle. This time we're using a slightly different prediction of the ionosphere, and we're looking a bit further before the earthquake, so a day in advance. What we'll see here in the video is that generally the model starts off performing pretty well, wiggling about in the yellow zone. But then about 20 hours before this earthquake, the model has a preference for being below 0 and mostly within the orange zone. Something is not normal in this central region. And sure enough, in this case, there was an earthquake later on. This is our most promising approach so far, but we do need further work to validate it. We just have time for a quick summary of our whistle-stop tour. So firstly, we have confirmed the presence of consistent patterns before and after earthquakes and linked these to where they happen in the world and their type of earthquake. Secondly, we built a pipeline to generate global machine learning ready data. And this pipeline is open source and ready to ingest whatever data people can throw at the problem in the future. We've also tested an array of AI models to directly identify and forecast earthquakes. And these models perform excellently on synthetic data, but ultimately we need more or better data. And then finally, we have an indirect approach that in fact may work better in this case. Thank you very much for your time, and thank you to our sponsors and our faculty.
Amazing team, and I feel a bit. I don't envy the panel. We're going to go into the white panel now for basically being shown the Mona Lisa with both of those 2 projects, and then having to respond to it. But I wanted to introduce our white panel. I know we've got Lika here, who we've already met from NASA headquarters. Massey, who's distinguished technical director, applied AI at Google Cloud. Tom Berger, Space Weather Technology Research and Education Center. Of course, Bill as well. So yeah, just really quite amazing to see those 2 results back to back, and really would love to just get your first impressions and what you think. And it looks like we've got Massey there. Do you want to take us or set us going, Massey?
Thank you. And so, first of all, congratulations to the teams. This is actually amazing results. I love actually, Lika in the introductory video actually spoke about data products. I think actually this is a great input from these teams. They're not just kind of advancing the status quo of research here, and to what we said actually at the beginning of the discussion, they're applying AI to science in a way that has never been done before, but also creating data that can be used then by other researchers to kind of further actually kind of this research and get more insights. And I think actually that's actually that kind of network effect that is going to make this even more valuable. It's actually 10xing the work that they're doing. I also kind of, congratulations on applying AI in ways that is so innovative. I mean, like I love NERF actually, for those who are not in the eye. It's something that kind of was published actually first time a couple of years ago. And those teams are already applying it to kind of solving scientific problems. So this actually is a great feature of FDL, of like bringing together those people and advancing scientific research in ways that are kind of so important. I would say that, I think actually understanding the sun better and kind of solving some of those problems, it's really important. The sun is definitely kind of, our powerhouse. It powers life on Earth. And it's incredible. I mean, every time I talk to Lika and some of the solar scientists, how still actually kind of how lot actually we have to understand of the sun. And part of the problem is that it's a super complex system. And so I think it's the idea of applying AI to look inside the haystack is great. And kind of I love the way in which the teams have used data and computation to do that. So congratulations.
Thanks, Matty. So speaking of heliophysicists, do you want to, Lika and Tom, do you want to respond to what you just saw?
Sure, go ahead, Lika.
Well, I think in the introduction, I kind of tried to capture what these two groups have been attempting to do, and actually seeing the demonstration is pretty breathtaking for me. And yes, these are perhaps small steps, but think of the quantum leaps they will make in the near future. With the EUV, we have mission concepts where we want to send missions to the poles of the sun, really to get that magnetic field measurements. It's a critical measurement to really complete a more fuller understanding of the magnetic field, how it's created, destroyed, preserved, how it creates the very environment we live in, and to see the group kind of utilizing observations that we have taken for so long, trying to synthesize them and create this synthetic view of the sun. I think this is powerful stuff. This is actual physics that we support with our research and analysis tools. I think there's so much to come from this particular area of investigation, because EUV, extreme ultraviolet, affects us in so many ways, even as going far away from our own planet to Mars or other exoplanet environment someday that we might come upon. This will be sort of the benchmark type of measurements that we will need. And with the seismic insights, it is just that. It is telling us how difficult the problem is. And so this was really sort of a quick take on bringing everything we have to date that was available to the team over these 8-week periods. What we have to do now is really pull in more data. Larger scientists, this will require much bigger effort to really pull those very faint sort of signals that exist. And it's not ionospheric disturbance, some of which is really propagated through the sun, how that impacts earthquake. But earthquake perhaps leaves some signature in the ionosphere too. So often we think sun as the driver. It is the most powerful driver, but there are disturbances also affecting this ionosphere, a very important region for space weather that is coming from below. Amazing stuff. Thank you.
Yeah, I'll echo that. Thank you to the team. Great job. I really enjoyed the presentation and watching it develop. I would add on to what Lika said in that the earthquake prediction may have been difficult, but what you really did was explore the parameter space and show. I really like the exploration of the complexity of models versus the phenomenon you're looking at, because that's very valuable to us researchers in solar flare physics as well, and solar flare prediction. That's exactly what we're up against. Solar flares are rare episodic phenomenon. They occur on these different scales. And having this sort of exploration of a similar phenomenon come out with a result that we can use, namely that the complex models don't necessarily do better, we should maybe be looking at smaller models, simpler models, was really helpful. And I'll just finally add that the ionospheric post-earthquake signal can be used to forecast tsunamis as well. So you've shown a really useful signal that can be used for not only predicting earthquakes, but predicting the effects of earthquakes after the event itself. So really great job.
Thanks, Tom. Yeah, I think the fact they've got a tsunami detector working is a really big achievement just in itself.
Yep.